Welcome to all my learning peeps. We're going to do another dynamics problem today. It's also related to kinematics, and in today's problem we're going to be looking at a curvilinear type of motion. The last problem we looked at was a projectile type of motion. And here is a problem that I've selected out of Hibbeler's 13th edition textbook titled Engineering Mechanics Dynamics, copyrighted in 2013. Problem 12-121, found on page 61. And basically you have a roller coaster as pictured here. The track of that roller coaster is a parabola. It is given by the graph y equals 0.01 times x squared. And you have a drop going from point A down to the point of interest for us is point B in this particular problem. Point B, as you can see, is located 30 meters horizontally to the right of the origin. The origin is placed at the bottom of the drop there, as you can see. We are given a couple pieces of information. One is the instantaneous speed of the roller coaster car at point B is told to us to be 25 meters per second. And then we are also given the fact that it is increasing at a tangential component of acceleration by the amount of 3 meters per second squared at that point. And so what we want to do is find both the magnitude and the direction angle with respect to the x-axis of the total acceleration at that instant. Okay, so, well, curvilinear, and also, as I mentioned, you probably know by now that I like to make little side notes before I get into the mathematics and the science of the problem itself, and I always try to give a small side note that is aligned with the topic that we're talking about. So I was thinking really hard, curvilinear, what does the Bible say about curves? And one thing that stood out from my searches about that is this idea of things increasing more and more rapidly. And so if you were to look at the prophecy of Daniel, which was written about 2,500 years ago, about approximately 500 years before Christ, you see these interesting verses, pair of verses. In particular, you see in Daniel chapter 12, verses 4 and 10. Let me just read that. Verse 4 says, "But you, Daniel, keep this prophecy a secret. Seal up the book until the time of the end, when many will rush here and there, and knowledge will increase." Let's just take that for a second. As I was thinking about that, you see an exponential increase in knowledge, just as Daniel was prophesying about, 2,500 years ago. And isn't that interesting? Here is a little diagram that I took from the website cited below. And if you look, well, I'm old enough to remember way back when a megabyte used to be something to talk about, and that's 1 followed by 6 zeros, or 10 to the power 6 of data storage, let's say. But then we moved over 1,000-fold to a gigabyte, and then we were all awed because we thought a megabyte was something back in the day, and then a gigabyte. Well, we're probably more, at least on a personal level, at the terabyte stage, which is 1,000 more than the gigabyte. But look how quickly things are being multiplied 1,000-fold over. So we're headed to petabytes and exabytes in the not too distant future. And the website that I was checking out, essentially the thesis of that website, and again, if you're interested in seeing what I'm talking about, the link is down below in blue. But basically, as the title of the article suggested, that knowledge was doubling every year, approximately, and then the thesis was that it's soon to be every half of a day, 12 hours. It's also interesting in this diagram, if you look at the scale, if you go back when a megabyte used to be something in the scale of what we're talking about, that could have been the size of an ant, but then you look at a gigabyte, and that became the height of a person, so far larger. And then at the stage we are in, probably personally, is at the terabyte stage, which is the length of the Auckland Harbor Bridge. And where we're headed is the length of a country, New Zealand, and then eventually that exabyte at the far extreme right is the diameter of the sun. So just to give you a little, putting things into a certain proper scale. Then you look at verse 10 out of Daniel chapter 12, and let me read that, and it says, "Many will be purified, made spotless and refined, but the wicked will continue to be wicked. None of the wicked will understand, but those who are wise will understand." So the message for the day is be wise. See that something written 2.5 millennia ago bears very nicely in today's world, and isn't it spot on? And as a matter of fact, there are many more things that Daniel the prophet has written in his little book in the Old Testament of the Bible, so I would urge you to check some of that out. But it's just stunning and astounding to see in today's world how true these things are. And along with the issuance of being wise, I would encourage you to also consider that scripture that says, "The beginning of all wisdom is the fear of the Lord." So if you don't have a fear of the Lord, according to the Bible, you're not being wise at all. So the opposite of being wise is being a fool, and it's not me who's saying that. So I would urge you to check out that one question video that I've produced. It's a 12-minute video, and the link is appearing right now as I speak for you to check out and see how you can go about fearing the Lord properly and obtaining salvation for your eternal soul. Okay, very good. Let us go and jump into the mathematics of this problem. So once again, this is the problem. Let's list for us what we are given and what we're to find. So we were given that the graph of the parabolic tracks of that roller coaster. It's y equals 1 over 100 essentially times x squared. And we were also told the instantaneous velocity, let me call that v sub b, and that was 25 meters per second. And then we were given the tangential component of the acceleration at that point. Let me call that a sub t sub b, and that was 3 meters per second or 3 meters per second squared. And we want to find, essentially we want to find the total acceleration instantaneously at that point of the journey of the roller coaster car down the tracks. And the other thing that is of interest corresponding to that total acceleration is what is the angle of the acceleration at b. So let me call that theta sub b, and then I'll also say sub acceleration because this is an angle related to the acceleration of that. And this is, let me just write this out in case you're wondering what I'm talking about. So this is the angle of acceleration, at b with respect to the x-axis. Okay, so W period, R period, T period is my abbreviation for with respect to. Okay, let's go ahead and jump into trying to solve this, and I think it's actually the solution is pretty simple. In fact, the diagram that we'll see, and I'll draw this out so you see what I'm talking about, is a little more involved in my mind than the mathematics. But anyway, so we are given y as a function of x, and here it is. It is to say that y is 0.01 x squared, and so I can go ahead and differentiate this once and then twice over. So y prime is equal to, notice that the 2 comes out in front, so it becomes 0.02 x, and then you knock down the power of x by 1, so 2 minus 1 is 1, so x to the first power. And then let's take a second derivative of this, and if you do one more derivative, it's just going to be a constant 0.02, okay? And you may say, well, why did you do that? And I'm going to explain the reason for that here in just 1 second. Before I do that, let me explain one other thing that you need to keep in mind as we try to solve this problem. So I'm going to do a small aside just so that we make sure that we're all on the same page with a concept, an important concept. So imagine you have your x and y axes, okay, and you have some parabola, and it doesn't really matter what this parabola is. I always like the parabola, the simple parabola y equals x squared. Let's pretend that's what that is, and it doesn't really matter though, okay? Now, if I pick a point, any point out here, let's say some value of x, I'm going to call this x tilde, alright? And I come up and see what is the corresponding point on the graph at x tilde. I think we all know from our basic calculus lessons that if I were to take the tangent of the graph at that point, I can draw it, let's say, like this. So this is the tangent of graph with respect to point at x tilde. Okay. The point I wanted to make in my aside here is that we all know that that is gotten by looking at y prime. Okay, that's basically the slope of that line is gotten by taking the derivative of our graph y prime at that value x tilde in this particular case. And moreover, the angle here, this angle, which I can call, I'm just going to call this, just generically I'll pick some Greek symbol to denote the angle. Let's suppose I call this beta for now. If that's beta, then I know that the tangent of beta, so this was one point, that that red line that is tangent to that point of interest is gotten by y prime, the derivative, the first derivative of the curve. And then the other point that I wanted to make in my little aside here is that tangent of beta is equal to that y prime at x tilde. Okay? This didn't come out so well. Let me write it over here. Tangent of beta is equal to y prime evaluated at that point. Okay, these are the 2 points that I wanted to make. If I wanted to make one more point, it would just be something from simple geometry, and that is to say that notice also that this is also beta right in here, and that's because those would be vertical angles. Okay, so we know that vertical angles are equal. So anyway, enough of that little aside, and like I said, the actual math and so forth in this problem is really not that difficult, so I think we'll get through that pretty quickly. The other thing that we need to know is, and again this comes from calculus, is the idea of curvature, and this is one of those equations from calculus that I've just memorized because in engineering we see this come up from time to time, and so I just had memorized that. And curvature is usually given the lowercase Greek letter kappa. Okay, so kappa is the absolute value of y double prime over 1 plus y prime squared, and all of that on the denominator is raised to the 3/2 power. Okay, and the other thing related to curvature is the idea of radius of curvature. And you may see different symbols used for that. Very often in calculus books they'll use rho. I could use r. It's really not that important, but okay, so let's just go ahead and use rho here for in keeping with what you probably have in your calculus textbook. So the corresponding radius of curvature then is 1 over kappa. So if I were to flip that equation up above, the denominator becomes the numerator and the numerator the denominator. So I get 1 plus y prime being squared, all of that raised to the 3/2 power divided by the absolute value of y double prime. Okay? And now you see why I took the first and second derivatives of y, because we're going to work with this here now. Okay, so y prime evaluated at that special point where it is x is equal to 30 meters is actually very simple to do. Well, we know what y prime is. We figured that out here. So if I put that in here, I'm going to get that it's 0.02 times 30 meters, and that's going to be 0.6, right? So 0.6, and also y double prime evaluated at that very same point is a constant. So I don't even need to really figure anything there because it's a constant. All right, very good. Now we have these pieces of information, and I can find the radius of curvature at that point B. So therefore, the radius of curvature at point B is exactly what we were talking about. It's 1 plus y prime being squared. Y prime is 0.6 squared. All of this is raised to the 3/2 power, and y double prime is a positive constant, so it's just 0.02 on the bottom. And if you were to crank this out on your calculator, you should be able to find that the radius of curvature at point B. Okay, let me see if I can write this a little better. Radius of curvature at point B is rho sub B is equal to 79.30 meters. Okay. Now, you may say, well, why did you do that? Well, you probably know from just basic physics that the centripetal acceleration in this particular discussion, I can call that my normal component since we have the tangential one. But the normal component is going to be very much like your idea of centripetal acceleration. It's just v squared over the r, or the rho in this particular case. So we have v sub b, which was given to us, squared over rho sub b, and that is equal to, we were told that v sub b is 25 meters per second, so that's 25 being squared, and rho sub b is, we just computed that, it's 79.30, and if you do that on your calculator, you'll find that the normal component of the acceleration at that instant is equal to 7.88 meters per second squared. Right? And then we're almost home in answering the first of the two things that we need to look at, namely that the total acceleration at B, so let me write this out, total acceleration at B, we can find by the Pythagorean result, namely that the total acceleration there squared has to equal the sum of the squares of the normal and the tangential components. Okay, so in other words, if I take the square root of that, the two sides, I can find the total acceleration at B is going to be the square root of the tangential component at B squared plus the normal component of the acceleration at B squared. And so we get 3 squared for the tangential component that was given to us, plus the one that we just computed right now, 7.88 squared, and then you're taking the square root of the sum of those squares, and you find that the total acceleration at point B is 8.43 meters per second squared. Okay, and what remains for us to figure out now is what is that angle of the acceleration So if this is the acceleration at point B, what is this angle right in here, which we were calling theta b of acceleration? Right? We don't know that quite yet, but it's not really difficult to find what that is, and let's go ahead and figure that out, okay? For doing that other part, and this is what I was saying at the beginning, that this next part is a little bit more involved, but it's actually pretty simple. But the drawing, you need to be careful with the drawing. So in anticipation of that, I went ahead and drew the figure ahead of time, and here it is. I've blown it up greatly. This is, of course, point B right here, which I've tried to line up right underneath the drawing of it, although that doesn't really matter a whole lot. And notice that we already computed the total acceleration a sub b, which is this arrow or this vector, if you will, of what did we say? It was 8.43 meters per second squared. Okay, we already just computed that. Now the question then is, what is this angle right in here? This one, theta sub b sub acceleration. That remains to be found. But based on the aside that I did a moment ago, this isn't really that difficult to do, because this right here, this angle, let me do this in red so you see what I'm talking about. This angle right in here, we can find that pretty simply. Notice that this, okay, before I do that, let me back up just ever so slightly here. Let me say that this thing right here, let me scroll up a little. This is the tangent. This is the slope of the tangent at point B. Okay. So, so this angle right in here. Let me erase this. This angle right in here is what I was calling beta in my discussion of the aside, and we said that this angle beta is this angle beta by virtue of those two angles being vertical angles. And so, well, what is this? The slope of the tangent line here is simply equal to y prime at that location B. Okay? Well, we know what that is. We know that that was equal to 0.6, right? We computed that up here. We said that y prime at location B is 0.6 right here. Alright, so that we already did, and we know from the aside that we were talking about that the tangent of this angle beta is equal to y prime evaluated at B, which happens to be 0.6. So I'm in a great position to figure out what beta is, and I went ahead and computed that. So beta happens to be, let me see, beta happens to be 30.96 degrees. Okay. A couple other things that I should write on my diagram in case you're not following some of what I'm doing here. This vector right here, let me do this in pink. Okay, so this vector right here, I hope you'll understand that that vector right there is the vector that is essentially the centripetal or normal acceleration. So this is what we were calling a sub n at B, and we knew that a sub n at B is 7.88 meters per second squared. And then this other vector here, which is hiding down, I need to scroll up a little bit. Okay, this vector right down here, which is kind of hidden in the red, is your other component, which is the tangential component, right? A sub t sub b was given to us to be 3 meters per second squared, and that's how we found by Pythagorean's result AB, the total acceleration there. But now we found what beta is, and what we're really after is what is this thing right here. What is theta b of acceleration? And Well, what is this angle right here? Let me do that in, let me do this in green. What is this angle right in here? Okay, that angle right in there, I hope you will understand from basic trig that this angle is, let me call that phi, since I have already used another Greek letter beta. Phi is equal to the arctan of the normal component of the acceleration at b divided by the tangential one. Okay, this is just basic trig. And so phi equals arctan of a sub n, we said, is 7.88. And a sub t sub b is 3. And if you do that on your calculator, you'll see that phi comes to 69.16 degrees. Right? So I think we're in business, because what we wanted to do is figure out what is theta sub b acceleration. So let's go ahead and do that. So theta sub b acceleration is equal to the phi minus the beta, right? Do you follow how I did that? If you look at phi, it's the green angle that goes from all the way from down here all the way up there, and if I take away the beta, I'm going to get the theta sub b acceleration left over. So this is going to be 69.16 degrees minus the 30.96 degrees, and so theta sub b of the acceleration is equal to, finally, 38.197 degrees, and it's going in a clockwise orientation as drawn in the figure there. And so let's go ahead and summarize what we found. So the answer to this question is going to be the total acceleration at B is 8.43 meters per second squared. It is acting, or the orientation of this is going to be at an angle which we've called theta sub b acceleration of 38.197 degrees, going in a clockwise orientation there. Okay, so here is the answer of the problem statement. So again, this was a pretty nifty problem. Also, let's just talk about what we did here. We listed what we were given. We said in terms of symbols, we said what we need to find. We then drew upon some of our knowledge in basic calculus, namely that the slope of the tangent line is the y prime, and then geometrically or trigonometrically we can find the angle it makes with the x-axis corresponding to that. And then we also drew upon our knowledge of this idea of curvature, and that the fact that the radius of curvature that corresponds to the curvature kappa is just the inverse. So 1 over kappa is the radius of curvature. And we took a couple derivatives. We were able to plug it into the equation for the radius of curvature. And then we were able to find the normal component of the acceleration. We were given the tangential component. And then if you go to the diagram, you see that it's just nothing other than the Pythagorean result to find the total acceleration, because the square of the total acceleration is equal to the sum of the squares of the tangential and normal components. So, and then we did a little geometry to figure out the corresponding angle. Okay, wonderful. Hope that made sense to you, and if you have any questions, please do write me and I'll do my best to answer your questions. Thanks for watching, and we'll see you in a future video.